Okay, there you go. So we're going to start single transistor amplifier. Okay, so we're going to do BJT amplifiers and MOSFET amplifiers. Okay, typically BJT amplifiers tend to have much bigger gain. Their fundamental amplification is coming from beta, which is the current amplification factor, as opposed to MOSFETs. Okay, their gain is mostly coming from the transconductance GM, which is relatively small compared to BJTs. Okay, but they're more they're used much more often ubiquitous. Okay, MOSFET amplifiers for a lot of other advantages that BJTs don't have. Okay, so before and we talked about some of these already. The different kinds of amplifiers. Okay, a voltage amplifier, a current amplifier, transconductance, and trans resistance amplifiers. Okay, I'll come back to talk about this. For now, I want to start with the end in mind. Okay, if you happen to read this book, The 7 Habits of Highly Effective People by Stephen Covey, it's a very good book. Okay, it's a self-help genre, and one of the 7 habits of highly effective people is to begin with the end in mind. You don't want to meander and lose sight of what your goal is. So it's always best to begin with the end in mind. How do you want people to remember you? Or let me put it in my perspective. How do I want people to remember me after I am dead and gone? And that's the kind of life I want to live. That's the philosophy of beginning with the end in mind. That can apply here as well. That can be used here as well. What is it that I'm trying to achieve by looking at, because these simplifications, these calculations are dizzying. It's quite easy. It's extremely easy to get lost in this corn maze of numbers. Okay, so what I want to do is to really simplify things for us. Okay, there are 3 kinds of amplifiers that we will look at: common emitter, common base, common collector amplifier. This is for BJT amplifiers. Okay, so for the MOSFETs, okay, there is a parallel between MOSFETs and BJTs, right? So as you can see, I'm beginning with the end in mind. I'm starting with the summary first. Okay, there's a common source amplifier, common gate amplifier, common drain amplifier, corresponding to common emitter in BJT, okay, common source in MOSFETs, okay. Common gate is similar to common base in BJT, okay. Similarly, this is common collector in BJT. Okay, there are 3 configurations. Okay, as you can think about, as you can see, imagine, there are 3 terminals. Okay, let's say I apply the input on this side. Okay, input is applied, and let's say I tie this to ground, tie the emitter to ground. Okay, the input is applied between the base and emitter. Okay, let's say the output is taken between the collector. Okay, it's not a voltage source as it is a voltage that I'm measuring, V output. Okay, input is applied on the base emitter, output is measured on the VCE. Okay, as you can see, the emitter is showing up on the input side, and the emitter is showing up on the output side as well. That terminal is common to the input and the output. Okay, it doesn't necessarily have to be ground. It can be any other voltage. But as long as the input is measured between the base and emitter, and the output is between the collector and emitter, we like to call that, we call that as common emitter. On the exact same logic, I can have common. So in a common emitter, input is on the base, output is on the collector. Okay, emitter is the common terminal, hence the name common emitter. Okay, similarly, we can think about common base and common collector as well. I'll talk about that. But the idea is any single amplifier configuration in BJT has a corresponding dual in the Mosfet regime. Okay, so let's say common emitter or common source amplifiers. Common source amplifier is MOSFETs, common emitter is BJT, right? Common emitter amplifier is the bread and butter gain stage. Okay, even for your project, okay, lab 8 project, the kind of amplifier that you're building is a common emitter amplifier, right? There's a common emitter amplifier that you're building. You have to design the resistances RC, RE, RB so that you match certain specifications. Okay, so that's the idea. Common emitter amplifier where the input is applied at the base. This is the bread and butter gain stage. You can get really good gain, but the gain is negative. The gain is negative in the sense that the output is an inverted amplified version of the input. Okay, this is your input. Okay, the output is going to be something like this, a magnified inverted version of the input. Okay, that's the idea of gain. Okay, it has both high input resistance and high output resistance. Okay, it has a high input resistance and high output resistance. It provides for both high gain and good RI. So it's good for voltage inputs, okay, and not a good source to drive low resistance loads, okay. So let me summarize common emitter and common source stage. Good for gain and good for voltage inputs, bad for driving a low, small load. Okay, for example, if you wanted to drive an amplifier or a speaker, okay, the common source stage cannot directly do that. Okay, you lose a lot of signal. Remember the commissions that I talked about? There's a payout, there's an initial investment. You end up losing a lot in the commission. Your payout through a RL or a speaker is going to be really, really small. You're going to lose quite a bit in the commission. Okay, in the very beginning of this semester, we talked about the notion of signal loss that happens in an amplifier because of source resistances, output resistances, so on and so forth, right? As you'll see, the idea is that when you have an output voltage and a really large output resistance and a small load resistance, okay, a lot of your amplified signal, V amplification, is going to be lost across this large RO, and only a small amount is going to show up in the load resistance. Okay, that's a bad thing. You want a whole lot of voltage signal showing up across the load resistance. Okay, so you cannot use this directly to drive loads. That's the bottom line. Okay, so common emitter amplifier and common source amplifier, they provide very good gain, but they're bad for driving small loads. Okay, let's look at the other extreme. Okay, this guy, common drain amplifier. Common drain amplifier, the gain is really not much. At best, 1. At best, 1. What do I mean by that? What I mean is if this is your input, okay, your output, forget about amplification, it's going to be attenuated. It's going to be smaller. So you're not getting any amplification out of it. You're attenuating the output, but not too much. Hopefully, the gain is hopefully close to 1, but less than 1. Okay. Hopefully, and the gain is positive. Because the gain is positive, you see the input and output are in phase. Okay, so that's one of the characteristics of the common drain amplifier, which is also common collector amplifier in BJT. Okay, so positive gain, meaning that the input and output are in phase. You're not getting any good gain. But the real advantage is that it's often used as a unity gain buffer. Okay, it's a good choice to drive low resistance loads. So like I said, think of a common source stage, and then there's a load, RL. Okay, as I mentioned earlier, you cannot simply directly tie them together. The common source cannot drive a load. Okay, so what you do is you insert a common collector, common source or common emitter, right? So this is going to be a common drain, common collector. So what you do is you can use this guy to drive loads, good for driving small loads. Okay, that's the idea of common drain. When you're building a multi-stage amplifier that needs to interface to an external load, capacity, typically they have external loads have a small resistance, 50 ohms. A speaker, for example, has a small resistance. Okay, what you do is to use common collector. Okay, common collector of a BJT or common drain of a Mosfet as an intermediate stage, as an output stage amplifier. Okay, so there's a gain stage. The bread and butter gain stage is common emitter or common source amplifier. The output stage is typically a common collector or common drain amplifier. Okay, common collector in BJTs, common drain in MOSFETs. Okay, because this is good for driving small loads. Okay, so that's about common drain amplifier. So let's look at the common gate amplifier, which is in between. All right. Okay. Okay. All right. So the common common gate amplifier, and in BJTs it is common base amplifier in BJTs.
Professor, so common means that thing is grounded, right?
It's grounded, or that's both on the input and output ports. Mostly it may or may not be grounded. It simply means that the input is applied between, this emitter is common to both the input side and the output side. Okay, sometimes it can be grounded, sometimes not. Okay.
Okay.
Okay, we are looking at the different kinds of amplifiers, 3 different kinds of single transistor amplifiers. Okay, single transistor amplifiers. Common gate, okay, can achieve a high positive gain. So let me color code this differently. Common, this guy is good gain, decent gain, and low input resistance and high output resistance provide high gain. So good for current inputs, not a good choice to drive resistance loads. See, cannot. It's the exact same problem as this guy. Okay. Okay, I might as well duplicate that. Okay. It is bad for driving small load. Okay. It turns out that the only amplifier that is good for driving small loads is the common collector amplifier or common drain amplifier. This guy, on the other hand, the common gate sometimes is used for cascode. Okay, that is when you add it in conjunction to a common emitter or common source amplifier. Okay, that's a little beyond the scope of our class. But when you get to EEE 109, this is where you'll see multi-transistor amplifiers, multi-stages. Okay, a series combination of common source and um, common gate produces a really interesting stage called cascode stage, where the output resistance is going to be really large, almost the squared of the intrinsic resistance. So it can provide a lot of gain at the cost of voltage, headroom, and leg room. That's a little beyond the scope. So the idea is, here is the summary that you want to remember. Okay, common emitter amplifier is a bread and butter gain stage. It is bad for driving small load. Okay, common collector amplifier, on the other hand, it doesn't provide a whole lot of gain. Okay, common collector amplifier does not provide a whole lot of gain, but it is good for driving as a unity gain buffer. Okay, but then there is a common gate amplifier, or common base BJT. Okay, let's see if I can go back and show this to you in equations. Okay, let me show this to you in equations. So we're really going backwards. Okay, you're really going backwards. Okay, so here is the emitter follower, which is also the common collector stage. Okay, okay, don't get lost in these numbers. Okay, the only thing that you want to recognize is the numerator, beta plus 1 times RE, and the denominator, beta plus 1 times RE. They're almost the same. As long as RB and R pi are small, when they are small, this is approximately equals to beta plus 1 over RE by beta plus 1 over RE. Not quite 1, almost close to 1. Okay, approximately 1. That's exactly what we found out, right? The common collector amplifier has a gain that is almost close to 1. Okay, let's see if that is what I mentioned earlier or not. Okay, common collector amplifier in BJT has a gain that's almost close to 1. Okay, so I'm not going to go back and forth between these slides here. You just have to trust me when I say that. Common collector has a gain almost close to 1. And if we go back to common collector, and I apologize for this jumping around. Okay, the common collector stage. Okay, and we'll see the configuration of this a little bit more carefully. But for now, I want to grasp the big picture. Okay, beta is a large number, right? The current amplification factor, beta is a large number. If no value is given to that, we were happy to take a value of 100 for that. Okay, so what you can see is you're taking RE, multiplying that by 2 orders of magnitude, increasing it 100-fold. Okay, so that's going to dominate the denominator. So it's going to, the overall function is going to be almost close to 1. Okay, as you can see, this is close to 1, but definitely less than 1. Okay, because the denominator is less than the numerator. Okay, so you can see that it's good for not good for a whole lot of gain, but a decent amount of output drive. Okay, it can drive a small output loads. Okay, we'll come back. Okay, let's see the common collector amplifier. The common collector amplifier has the gain. Okay, has a gain of beta plus 1 Re by Rb plus R pi times beta plus 1 times Re, what we just looked at. Okay, and then we'll come back to talking about all of these resistances shortly. Okay, that's the common collector amplifier. Let's look at the common base amplifier. Now let's see, before we move on, let's carefully look at why this is called the common collector amplifier. Okay, look at the input R, that's the resistance looking into the input. The voltage source right there, that's the input, right? That's input. The input is applied between the base and collector. This is ground for signal purposes, for small signal purposes, because the DC value is not changing. That can be considered as ground. Look at the output. Where the output is on the emitter. So input on base, okay, output on emitter. That's the emitter, right? Output is on the emitter, collector, base, right? So the collector terminal, that's common, okay? So input is on B, base and collector. Output is on CE or EC. Therefore, we have a common collector amplifier. Input is on the base, output is on the emitter. The collector terminal is common. Okay. This is also called a this is also called an emitter follower, because there's a really, what do you think is the VBE here if it is operating in saturation region?
Saturation high.
Sorry, my bad. If it is operating in linear triode region, what's this voltage between the base and emitter?
It's reverse biased.
It's forward biased.
Base emitter is
This guy is reverse biased. This
yeah,
guy is
collector
forward
emitter.
biased, right? Yes. So what value would that be? 0.7 volts, right? So if I were to increase the voltage on the base, okay, the emitter voltage simply tracks along, okay? If the base voltage VB was 1 volt, okay, V emitter, the large signal V emitter, let me be very careful here, V base, V emitter is going to be 1.7 volts. Okay. Similarly, any small signal increase in the bias voltage, the base voltage, is going to show up on the emitter voltage as well. So the emitter voltage is going to simply track the base voltage, hence the name emitter follower. Does that make sense?
Professor, how do we get 0.7 over there?
Remember the forward biased diode?
Yes.
The voltage, the approximation for the voltage across the terminals of a forward biased diode is 0.7 volts. So in the DC large signal model for a forward biased diode is an approximation of 0.7 volts. And that's why the large signal, the DC value is 0.7 volts over there. Okay, so that's going to show up in the AC signal characteristic, in the AC behavior as well. Any increase in the voltage on the base is going to increase, and that's probably why you're getting a gain close to 1. Okay, if you're increasing the input twofold, the output is also going to increase twofold. Okay, hence the name emitter follower, or it also, you can understand from the fact that the gain is 1. Make sense?
Yes.
Okay, so emitter follower It's called emitter follower because the voltage on the emitter simply follows the voltage on the base.
Uh, yes, like you said, like I'm still confused about point 0.7. You said it's the voltage drop across the diode. So like,
Yes.
are we using any diode over here? Like, how can we get point 0.7 at the base of?
Remember, BJT is fundamentally NPN.
Mm-hmm.
There is a diode right here, and there is a
Okay.
diode right here. You see, there is this. When I talk about diode, I'm talking about the base emitter diode. Okay, the base emitter diode as opposed to base collector diode. So there is a emitter base junction that is fundamentally a diode. Does that make sense?
Yes, sir. Thank you.
Yes. So that's the idea. So when I'm talking about diode, I'm referring to that's a very good question. Thank you for clarifying. The base emitter diode or base emitter junction is forward biased. Okay. The forward biased diode is really 0.7. Okay. That's the idea of common collector amplifier, or it's also called emitter follower because emitter voltage simply follows the base voltage. Okay, that's also shown by the fact that the gain is approximately close to 1. Okay, so if the input voltage increases, the output voltage also increases by the exact same token. Okay, that's the common collector amplifier. And I'm trying to make it as easy as we can. Just the intuition without paying attention to these calculations over here. Okay, we're not paying attention to the calculations over here. The intuitions, the results are important to us. Okay, look at the common base amplifier. Where is the input? Input is on the emitter. Okay, this is the emitter, right? That's the emitter. Input is on the emitter. Okay, where's the output? Output is on the collector, right? This guy is collector. Output VO is on the collector. Okay, that's the output. That's where you measure the output. That's where you see the output. Okay, so input is between emitter and base. Output is between collector and base. Therefore, I have the base that is common. Hence the name common base amplifier. Does that make sense?
Yes.
Okay, common base amplifier. Input is on the emitter, output is on the collector. Okay, you can see that the output is right there, the input is right here. Okay, input and out. Now you can look at the gain of this guy. And I ask that you can use your formula sheet. I'm okay with that, and I don't expect that you remember this equation. The idea is that the gain is V out over V in, and this is the relation we always want to know. V output over V in. Even earlier, V output over V in is the gain that we looked at. Is beta times RO by RB, that's the resistance in the base, plus R pi, the hybrid pi resistance, beta plus 1 times RE. Okay, so RO resistance on the output, which is the collector terminal, is roughly RC. Okay, because if you think about it, and I'll talk about that in a second, I don't want to get lost in the details here. So there is an R naught resistance over here. Okay, R naught in parallel with RC. That's the output resistance looking into this guy. Okay, roughly, there's some additional components in there as well that we want to that we can ignore. But the idea is a large resistance R naught in parallel with a small resistance RC. So the equivalent R out is going to be approximately RC. Okay. Questions, please. Questions about that. And that's the reason why the R naught over here is approximated as RC over there. Okay, everything else is same. And under certain conditions, you can approximate that to be VRC over VRE. Okay, now, most oftentimes assuming IC equals to IE, so on and so forth. Okay, but everybody with me so far? Let's see. This is a common base amplifier. Input is on the emitter, output is on the base. So I mentioned that the output, the gain, the overall gain takes this form, okay? And then I approximated RO, which is the output resistance, the resistance looking into this terminal, okay? RO, right? So let me clear this a bit, just so I can only highlight what I want. RO is the output looking into this resistance, okay? Into this terminal, okay? And I mentioned if you drew the small signal model, if you remember, there was R0 between the collector and the emitter. Okay, there was some R0 between collector and the emitter. Okay, the small signal model. So if you were to look into this, you would find R0 that is in parallel with RC, and we're going to look at the exact analysis, but you should have a technique to quickly look at the circuit and somehow approximate the resistances that are of interest. Okay, and then there is this 1 plus GM RE term present there as well, which makes R not much bigger. Okay, so a small resistance, so R naught multiplied by 1 plus GM RE, that is source degeneration effect. Okay, the emitter degeneration effect, R naught multiplied by 1 plus GM RE, a large number in parallel with a smaller resistance. So output resistance is approximated as RC. Okay, so the idea is the gain of this amplifier, can be expressed in terms of RC, the external resistance RC and the external resistance RE and RB. And to a large extent, this is what I want. I want my gain to be a function of external resistances so I can comfortably control them, okay, with reasonable accuracy and control, more importantly. Okay, so common base amplifier, a large internal resistance, okay, which is R naught in multiplication with 1 plus GM RE, okay, that in parallel with a smaller external resistance, okay, that gives you the gain. Common base amplifier, V output over V input. Let's see. Let's look at another one. Common emitter amplifier. Common emitter amplifier. Negative GM by 1 plus GM times RE. Beta R naught by RB plus R pi plus beta plus 1 times RE. Okay. That's the idea. The gain of this guy is negative. Pay attention to the fact the only amplifier configuration is a negative gain. This doesn't have a negative gain. This has a positive gain. The next amplifier doesn't have a negative gain. It has a positive gain. So the only amplifier that has a 180 degrees phase shift between the input and output is actually the common emitter amplifier. Okay, a common emitter amplifier whose gain can also be approximated in terms of the external resistances if we are careful to obey certain conditions. Okay, that can give us the maximum value RC over RE of the gain that we can achieve here. Okay, so this is the common emitter amplifier. It is called common emitter because the input is on the base. The input is between the base and emitter. VB is the input. Okay, the output, pay attention to the output. Output is on the collector. So input is on the base. Output is on the collector. That's the collector, right? So base emitter is the input, collector emitter is the output, common emitter amplifier. It's easy to see because it's common to both the input and output side. Okay, this provides a pretty good gain, provides a pretty decent gain. Okay, common emitter amplifier. So in the problem in chapter in lab 8, if you see an equation that looks like this, okay, all you have to understand is that we can control the gain that we want, the output to input ratio, how much magnification I can get out between the output and input based on the resistance RC, the external resistance in the collector, the resistance in the base, the resistance in the emitter, and then of course the small signal parameters R pi. Remember, we use them as a marriage between the large signal DC and small signal AC analysis. Okay, so mostly we can control them based on big knobs, RC, RB, RV, so on and so forth. Okay, so that's the idea of common emitter amplifier, the only amplifier with a negative gain. Okay, you can use them, you can use these formulas on a sheet of paper for your exam. Okay, so this guy, 1 plus GMRE, is coming from the fact that the emitter is degenerated here. So this guy is called a degeneration. Okay, it's called a degeneration. What's the advantage of that? Did we look at the advantage of this guy in the last class? I talked about the advantage that this resistance can bring in. Does anybody remember? Let's see if we can go back. It brings stability. Okay, stability as in it reduces the volatility in the bias point, the gain. Okay, let's see. When we do the voltage analysis, higher potential, that guy, there is an inherent feedback that I talked about. Okay, there, right here, an invisible feedback, inherently more stable. Remember, I compared a circuit, a common emitter amplifier, without a emitter degeneration, without a resistance in the emitter, as opposed to a resistance as a common emitter amplifier with an emitter degeneration. Okay, this resistance is called a degeneration resistance. Okay, I mentioned earlier, even for a constant IB, as beta changes, as beta increases or decreases, IC drastically increases or decreases. When there is, so the collector current is changing drastically to any small or large changes in beta. On the other hand, when you look at the circuit on the right, there is this resistance RE, okay, that kind of counteracts any sudden changes in IC. So go back to that lecture and see how it provides an inherent invisible feedback. Okay, all it does is when this increases, when this voltage increases, when the amount of the beta changes, even for the same IB, IC increases and IE tries to increase. When IE tries to increase, VE increases. Okay, as VE increases, VBE decreases, and that reduces the IC. Okay, so there is a mechanism to automatically counteract the effect of increasing value of uh, emitter or collector current as a function of. So the emitter or collector current is more stable in the degeneration resistance, in the degeneration case. Okay, so because of that, okay, the overall gain is lower. If I had had a common emitter amplifier that did not have this resistance, okay, that would have given me much bigger gain, okay, that would have given me the transconductance equals to negative GM, okay, but then I am losing some of the high gain, okay, instead of having a high gain, I prefer to have more stability in the gain. I prefer to have more linearity in the behavior, more less change in drastic change in IC as a function of IB. Okay, so that's the effect of degeneration. It's a little beyond the scope of this class. Don't worry too much if you don't understand that. All you have to understand is you can have configurations that don't have this RE and still have the emitter working fine. As a matter of fact, you'll have a much bigger gain there, except that the uh, the stability is not as good. You're not, it's not the best in the world. Okay, so three configurations: common collector, common base, common emitter configurations. Okay, now we can move on to talking about the different amplifiers, different, how we get these weird looking, horribly, horrendously um, devoid of intuition. Well, they're not devoid of intuition. We can gain some intuition into this, but then at the first glance, if you don't know what you're looking for, this may appear quite intimidating. Okay, so the way to beat them, the way to beat that is to start with the end in mind, understand the big characteristics, understand the relations, understand the relative values of this, and then delve deeper into the idea of arriving at this, deriving these expressions. Questions so far, please. Okay, questions so far, please. Okay, so let's. With that said, with that in mind, so here is the slide that shows all the three topologies. Okay, there's the common emitter where the input is on the base and the output is on the emitter. This is a common collector. Oh, this is the PNP version of it. So this is the collector, this is the base emitter. Okay, the PNP version of a common emitter amplifier is this guy. The PNP version of a common base amplifier is this guy. The input is on the emitter, the output is on the collector. Therefore, the common terminal is the base. Similarly, this is the common collector amplifier where the input is on the base. Okay, input is on the base, output is on the collector. Therefore, output is on the emitter. Therefore, this is a common collector amplifier. Okay, so the PNP topologies for single transistor BJT amplifiers. Makes sense? Questions?
So we like for common emitter, the input is on the base, output is on the collector. So like whichever terminal doesn't have input or output will be common, right?
Yes, yes, yes. So the input is really between B, B, E. The output is between V, C, E. Okay, so you can think of it as whichever terminal is not present in the input is the common terminal. You can say that, or the terminal that is common to both the input and the output. Okay, the reason I say it is common is think about this. Okay, let's look at the one on the left, the common emitter. Okay, when I supply a DC, constant DC bias, VCC, okay, and change a small signal input, is VCC going to change? It's not going to change, right? So VCC is assumed to be constant. Okay, so for a small signal perspective, in the eyes of a small signal, this guy does not change. Okay, the constant DC value of VCC does not change. So that is pretty similar to a ground. So when we are doing the AC analysis, if you don't agree with me, you can go back. Okay, maybe hopefully there is some analysis that I have shown here, the small signal analysis, where we ground. When we are doing the small signal analysis, we actually ground right here. Okay, so take a look. This guy, VCC, is tied to power supply, that terminal, right? So, but when you're doing the AC small signal analysis, for AC signal purposes, this acts as AC ground. Okay, for AC small signal purposes, that behaves like a ground. Okay, so by that argument, this is ground. Okay, the input is between base and ground. So the emitter is common to base emitter, which is the input. The output is VC and ground. Okay, VCE. Does that make sense? So therefore, we like to call this guy as the common emitter amplifier, or I can simply say, whatever is common, I'm not going to show it. Okay, so in this case, going back to your question, whatever does not show up, input is on the base, output is on the collector. I called it common emitter because I didn't explicitly show the emitter that is present in both the input and output side. Does that answer your question?
Yes.
Okay. Okay. So here is a yes.
Looking at those circuits, and I see that the common collector and the common emitter, they're pretty much the same type of circuit. Can you explain a little bit more about the difference between those two? And why that?
Yes. 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 It really has to do with this guy.
Oh,
Where
okay.
are you measuring the output? Okay.
Okay.
The output is on the collector here. The output is on the emitter here. That's all there is to it. The difference is that. Make sense?
I see. Thank you.
Other questions, please. Okay, NPN version of the three amplifiers. Okay. So to reiterate what I just said, the type of amplifier is completely determined by where the input is applied and where the output is measured. Okay, that's what determines the type of the amplifier. Okay. Now let's see. There are different kinds of amplifiers. So we're going back to square one now. Okay, different kinds of amplifiers. There can be a voltage amplifier. Okay, if your gain is always defined, gain is defined as output over input. Okay, if your output is a voltage, your input is a current, or input is a voltage, then you have a voltage amplifier. Okay, you have a voltage amplifier. Okay, similarly, if you have input is a current, output is a current, then you have a current amplifier. Okay, you have a current amplifier if the input is current and the output is current. Okay, you have a current amplifier. Okay, that's a current amplifier. Okay, transconductance amplifier is where your input is voltage and your output is current. Can you think of a circuit element, an electronic component that we looked at, which has this kind of relationship, this kind of configuration? Mosfet, remember? It was a voltage controlled current source. In response to the VGS that we apply, ID, okay? VGS minus VTH, the whole squared, right? So the input was the voltage, the output is the current, remember? This is the definition of a transconductance amplifier, okay? So it's conductance because V is IR, right? V is IR, okay? What do you get if you do I over V? So I bring V to this side and I bring R to the other side. That's going to be 1 over R. 1 over R is what? Conductance. Okay, so the input is voltage, the output is current. You have a transconductance amplifier. Okay, so let me write it out. GM, okay, GM, G sub M, the transconductance amplifier gain is input voltage in the denominator as opposed to the output current. Okay, that's transconductance amplifier. And now you know why we call it transconductance, because the input is because based on the Ohm's law. Okay, I over V in represents a term that is that has the same units as conductance. Okay, it has the same units as conductance. That's transconductance amplifier. Now, trans impedance or trans resistance amplifier, there are different kinds of amplifiers. Okay, when the input, the gain is input to output over input, right? When the input is current, I in, and the output is voltage, V out, then you have what is known as a trans resistance or trans impedance amplifier. Easy to see. V is IR, right? R is V over I. When the input is current and the output is voltage, we have a trans resistance or trans impedance amplifier. Let's see if I can do that.
Like,
Yes.
if we want to give the example of current amplifier, what will be?
BJT is a current amplifier, remember? Beta. That's a good question. Thank you, because it reinforces. What was the definition of beta?
Beta.
IC over IB, right?
IB. Yes.
Right? The input is the base current. The output is the collector current. Do you have? Make sense?
Mm-hmm.
So that's current controlled current source, BJT, is a pretty good example of a current amplifier. Okay, there are ways to convert a current amplifier to a voltage amplifier, and that's what you do, as a matter of fact, in lab 8. What is fundamentally a current amplifier, BJT? You pass the output current through a resistance, output resistance, RC, and convert that to a voltage. Okay, so you can convert one kind of amplifier to another kind of amplifier. Okay, as a matter of fact, if you build the common source amplifier, you're taking what is fundamentally a trans conductance amplifier and converting it to a voltage amplifier by passing the current through. If you pass the output current through a resistance, you get a, so it's quite possible to easily translate one into the other. Okay, the example is BJT. So there is a trans resistance amplifier. Okay, a trans resistance amplifier that can, the output is V out, input is I in, that is trans resistance amplifier. Okay, and then the ideal conditions for these are shown here. Input resistance should be 0. Input resistance should be infinity, output resistance should be 0, so on and so forth. Okay, so here is the deal. Okay, the idea is that all of these conditions are based on the fact that all of these conditions are based on the fact that you don't want to lose any commission when you're or signal loss. Okay, when you're amplifying a signal. Let's go back to that. Okay, so these are some concepts, okay, that you want to understand. Okay, something like this, very, very, very similar to this, is what we looked at in the last class. Okay, in the very first class, as a matter of fact, in the very first week of the semester. Okay, let me remind you what we did. Okay, the analogy or the simile that I gave was to you was that you start with $1 million of cash. Okay, and you want to invest that. This stage, okay, this guy is your investment. Okay, that is your investment, right? So let me do that. Show it to be this guy. That's your investment. Okay, that's your investment. As a matter of fact, if I'm careful, this guy is my investment. Okay, now this is your initial, let's say, let's have some fun. What the heck? Okay, this guy is your initial cash on hand. Okay, V out, and I want to highlight it in green. Okay, V out, that guy is the payout that you want. Okay, payout. And the payout resistance is through this guy. That's the load. That represents the payout. Okay, and I mentioned earlier that there are, let me see if I can convert them to, I don't know, a different color. not color, investment. Okay, now these guys, okay, are source and are not. Okay, they represent your commissions. Okay, they are the bad component. R source represents the commission. Okay, let's see. Okay, this guy, there's some signal loss that's going to the broker. Okay, RS because of the voltage division. Okay, and R not. They represent the commission signal loss due to commission. Okay, so that's the idea. That's exactly what is happening here. V1 is the voltage that is applied here. Okay, so you start with your cash in hand, VN. Okay, that all of that is lost, not all of that, part of that is lost to commission here. There is that voltage division that's corresponding to the commission over here. Okay, that gets amplified. Okay, this guy, this V1 times R naught or this gets amplified. V1 is being amplified. V1 is being amplified by GM. So let me write it. V1 is getting amplified by GM. That's your investment component. Okay. All of that is your investment component. That's actually doing the company that is giving you the gains. Okay. Whichever company you invested in. Then there is another signal loss component. Okay. That is coming out from the voltage division at the output. Okay. So the gain output over input is your transconductance GN times your load resistance, so on and so forth. RAOY over RI plus RS, that represents the voltage division at the input. RO by RO plus RL represents the voltage division at the output. So for this kind of amplifier, you want the RI to be really, really large. Okay, signal loss due to the idea. So you want Ri to be really large as opposed to Rs. The source resistance should be small. Similarly, you want R naught, okay, R naught, the internal resistance to be really, really, really large, okay, so that you get most of the current flowing through the load resistance. Okay, does that make sense? So for okay, so for output current, whenever you have an output current and a parallel internal resistance, the parallel resistance should always be extra large. Okay, I'm going to make it really informal. I'm going to call it extra large. Okay, you want this source resistance that is in series to be extra small, petty. Okay, and you want this external load resistance that is in parallel. Anything that is in parallel, the commission resistance that is in parallel should be really, really large. Okay, the reason is this guy is producing current. Okay, this is producing current. You want most of the current to flow through the load resistance, meaning that this resistance R naught should be really so large as to only take a small amount of current through it and let a large amount of the current flow through the output RL resistance. Okay, so that's some intuition around how different amplifiers are modeled. Okay, questions, please. Questions so far? So on the other hand, if you had an amplifier, okay, where the output resistance is in series with a voltage source, okay, if you had something like that, then you would want the characteristics differently. You would want R0 to be small. Okay, you want the output resistance to be small, not large value. Okay, similarly on the input side as well. Okay, for so this guy, for example, our output, where the output is a voltage in series with a resistance, you want the output resistance to be ideally zero or as small as possible. Does it make sense? So that's the idea. If the output is a voltage output, you want the R naught to be zero. Similarly, if the output is a current I out, you want R out or the intrinsic resistance, okay, to be infinity. Questions, please. Questions so far.
Like, what device is best for the transfer resistance? Like example of transfer resistance.
It is possible to convert a BJT into a trans resistance amplifier. There are you can build different kinds of amplifiers. I can't think of one component, a circuit element that is inherently good as a trans resistance, but you can convert BJT into a trans resistance amplifier. Okay. Other questions, please. What other questions do you have at this time? Okay, let's see if I can throw some more light at this relationship. Okay, so we'll come back tomorrow and then we look at the calculation of this. How do you calculate RI? How do you calculate RB? So on and so forth. Okay, so as you can see, the RI is an important parameter. RO is an important parameter. Okay, RI and RO. Okay, all you have to do is the generic procedure for calculating the gain is to look at RI, look at RO, and do that. Okay. Any questions so far, please? And did I cover everything up top? Yeah, yeah. Different kinds of amplifiers. Other questions? Okay. So this is voltage amplifier. This is current amplifier. This is trans impedance amplifier. This is trans resistance amplifier. Okay. Let's see. Here are single transistor amplifiers. We talked about this already. Where the input is applied, where the output is applied determines what kind of amplifier configuration this is. Okay. Let's see. Single transistors of BJT amplifiers, when we have common emitter, common base, that configuration is determined by where the input is applied and the output is measured. What we want to do is, so look what I'm going to do. Even before applying any inputs, if I just look at the terminals, okay, let me call this the base. Let me call this the emitter. Let me call this the collector. Okay, so if you think about it, it is a BJT, a resistance, external resistance. Okay. You think about it, there is RC, RB, RE. Fundamentally, if you go back to the circuit above, okay, all these are identical. Okay, if you don't apply any of these inputs, let me do that. I'm going to do this. Okay, if you get rid of the inputs and the voltage sources and the outputs, okay, fundamentally they're all the same. Okay, resistance in the emitter base, collector. Resistance in the emitter, base, collector. Okay, so if I don't apply any external voltages at all, okay, if I don't apply external voltages at all, in terms of, in terms of just this circuit, okay, without applying any input and any output, it's just one BJT with an external resistance in the base, an external resistance in the collector, and external resistance in the emitter. Okay, what makes the difference is when you begin applying inputs. Okay, for example, if I were to pick a terminal, one of you, why don't you pick a terminal on where you want to apply the input?
Like emitter.
You want to apply the input on the emitter, right? So it's yeah. Emitter is good for output. Remember, see, this is a good current sink. So
So
you can
base.
choose. Say that again. So
Base.
emitter right here. Okay, I'm applying input on the emitter. Okay, you apply input on the emitter, and you want to look at the output. That's what you wanted to do, right? You wanted to apply input on the emitter. Okay, let's apply input on the emitter. And then you want to look at the output on the collector. Okay, because base is really not a good output terminal at all. Okay, we can, there are other permutations at all. So when you choose to apply input on the emitter, which you did, and I choose to apply the output on the collector, measure the output on the collector, then I have a common base amplifier. Okay, so the point I guess I'm trying to drive is, until you make that exercise, that choice as to where you want to apply the input. Okay, if you don't make that choice, they're fundamentally the same. Okay, they're fundamentally the same. That's exactly what I'm doing here. If I don't apply the inputs or the outputs, the circuit is exactly the same for all configurations. So what I'm going to do, the first step is to look at the resistance, looking into the base. Okay, I'm going to define that as RB. Okay, notice that the external resistance are shown using uppercase, R is showing uppercase, RC shown in uppercase. Okay, the internal small signal resistances are shown using lowercase. Okay, that should be a hint for you to understand that RB, RE, and RC are external to the BJT. Okay, this guy itself. Okay, R naught, GM V1, R pi. That's the hybrid pi model for the BJT, right? When we were doing the small signal analysis, I showed that you can represent the base emitter junction using R pi, okay? And then there is a emitter collector emitter, which is shown using a transconductance amplifier GM V1, and then R naught. R naught was the channel width modulation, base width modulation parameter. Okay, we talked about that. Okay, the external resistances are this guy. Okay, they're shown in capital letters. So what I want to find out is eventually to get a value for gain in each of these amplifiers. Okay, in order to get the gain for each of these amplifiers, I look at the GM and I look at the R out. The product of GM and R out gives me the gain. Okay, the transconductance times the output amplification. Okay, so I'll show you a generic procedure for finding. So the first step, I guess you have to take my word for it, and you'll see when we finish the analysis. The first step that is helpful to us would be to look at the resistance looking into the base. What is the resistance looking into the base? What is the resistance looking into the emitter? what is the resistance looking into the collector? Okay, what is the resistance looking into each of these terminals? Okay, that's what I'm interested in finding. Okay, so that's the resistance looking into the collector, resistance looking into the emitter, resistance looking into the base. Okay, let's see if I can, without going into the analysis, okay, if I can show you the result. Okay, resistance looking into the base. Okay, that's this guy. When you're looking into the base, okay, the resistance of that guy, this seems to be Re, that's the resistance in the emitter, multiplied by beta plus 1, okay, times R pi. Okay, this is a large number, this is a large value. And that you can see that the current going into the base is small, right? That's because effectively what it sees is, and when we do the analysis, we'll arrive at this result. All there is to it is writing KCL. There are 4 unknowns and 3 equations. So we have to get a ratio. So we apply test voltage, test current. Okay. So RB, resistance looking into the base, is resistance in the emitter that is reflected and multiplied plus R pi. Okay. If I were to apply 100 or 1 kilo ohms over there, okay, and then the beta value is 100, okay, and R pi value is, I don't know, 550 ohms, okay, then the base resistance R looking into the base is going to be a really large value, Re multiplied by 101, okay, the product of these two plus the R pi value. Okay, so the base resistance has a component of the degeneration that we apply, the emitter degeneration that we apply, okay, plus R pi. Okay, that's this guy. Instead, if I have an amplifier that was simply tied to ground, the emitter of that guy is tied to ground, then the resistance looking into the base would simply be R pi. Okay, but here we have an emitter degeneration. Okay, because we have an emitter degeneration, that emitter resistance, the emitter resistance Re is reflected up into the base and is multiplied by beta plus 1. So Rb is the resistance that I set out to find, and I got a value for that Rb, an expression for that, sorry. I got an expression for Rb. Okay. Now you can also calculate Rc, Ric. What is the resistance looking in to the collector, looking into the collector? Okay. See, the idea I have here is R naught, okay, into 1 plus Gm times Re. Okay. So this emitter resistance is showing up when you look into the base, and it's also showing up when you look into the collector. Does that make sense at all? If I did not have a source resistance or an emitter resistance, okay, what would be the value of the resistance looking into the collector? So let me ask you that question. Let me do this. Okay, what if I tied the emitter to ground and you are looking into the collector? What would be the resistance looking into the collector?
Will that be RO?
It'll be R0 because
Yes.
there's nothing else. Okay, but if you have an emitter degeneration, what happens is that seems to, is a magic here, R naught is multiplied by 1 plus GM RE. It becomes a huge number. Okay, and you want it to be huge, remember? If you wanted to, I mentioned earlier, if you remember, a current source, a parallel resistance. For it to be a good amplifier, you should have the output resistance, ideally infinity. Don't trust me? Let's go back. I'm going to slowly take you there. Okay, when the output is a current, when the output is a current, in this case and in this case, what do you want the output resistance to be? You want it to be ideally infinity, a really large number. Okay, so go back now and see if that checks out. Let us see if that is indeed the case. Okay, we're going back here. The output here is a current GM V1 current source with a resistance in parallel. Okay, and if you will connect a load resistance here, RL, if you connect a load resistance here, RL, you want all of the current to be flowing through this load resistance. Okay, you want all of the current to be flowing through the load resistance. That means you want R naught to be extremely large. You want it to be close to infinity. Okay, and that is what is happening here. We're taking R naught, which is in itself a big number. R naught is a big number. And you're multiplying it with another huge number. Okay, so that is your effort. So the idea of adding your RE is that it improves your output resistance. Okay, now before we move further, why do you think R naught is a big number? What is R naught in the first place? And why, how can you not raise a question unless you know why? When I simply, how can you let me say just about anything I want to say without questioning that? Okay, I said R naught is a large number.
So
Are you
R
just
naught
going to
is
let me scot-free? Say that again.
like R naught is the output resistance. So like
Correct.
we want it large because we want more of the output on it, like voltage drop on
Correct. You want it to be large, but when I say it is, I want it to be large is different from it is large, right? Correct. You're right. I really want R naught to be large. And is it really large? Is something we want to verify. In your lab 6 or in your lab 5, I don't remember where you were doing the MOSFETs, okay? Where you were doing the MOSFETs, you were plotting ID as a function of VDS, right?
it.
Okay, and you saw a graph that looked like this.
Yes.
Okay, something like that when you simulated it in Spice. Okay, and that is slightly different from this guy. Okay, that's slightly different from this guy. Then, if you took the time to understand the slope here, what's the slope here? Delta ID over delta VDS. Okay, I called it as GDS or 1 over R naught. Remember the slope of this guy. the slope of that guy was 1 over R naught. What's the slope here? Is it small or large? What's
Small.
the slope? It's very, very small.
Mm-hmm.
So almost horizontal. Horizontal is zero slope, right? So just a touch slanting, but not quite. It's almost horizontal. So the slope is very small, meaning GDS is small. When GDS is small, that implies R naught is extremely large because that's the inverse slope, right? R naught is the inverse slope. And then you had to extrapolate that to, all the way up to early voltage. You remember the channel length modulation 1 over R naught is 1 over lambda ID, or early voltage over ID, so on and so forth. All that. Go back to your labs and understand that the slope, the ever so small, teeny tiny slope is actually the inverse of the R naught. Because the slope is small and the inverse of that is extremely large, that tells you that R naught is extremely large. Okay, so you can do the exact same thing for BJT as well, VCE versus IC. Okay, if you plot the same thing, you'll see the channel base width modulation effect. Okay, that represents R naught. Okay, I simply showed you this R naught. Okay, and you did not ask me what that is. Okay, that's the channel base width modulation or channel length modulation effect. And knowing the slope of the ID-VDS curve, I can tell you it is safe to assume that R naught is large. Okay, so that's the idea, and we can. There are some limitations to this approximation. There are some limitations to that. We'll talk about that. Okay. For now, I just want to provide enough intuition to you when you're looking into the collector. So the first thing you want to do, the first thing we did was to look at the collector, the base resistance RB. The base resistance RB is R pi plus. So what is in the base is R pi plus the resistance in the emitter multiplied by beta plus 1. Okay, the resistance in the base is R pi, and the resistance in the emitter is multiplied by beta plus 1. Okay, let's look at the resistance looking into the collector. Okay, that's what we are after here in this problem. Resistance looking into the collector is R naught, which is the resistance in the collector, multiplied by some factor of RE. Okay, some multiple of RE. Okay, and we can make some approximation 1 plus beta. We can approximate 1 plus GMRE to be beta, so on and so forth under some limitations. Okay, so that's IC. So there's only one more resistance that we have to understand. Okay, of the two resistances, resistance looking into the base, I found that out. Resistance looking into the collector, we didn't find out. I mean, to be accurate, I looked at it. Is a fair thing to say. Try to understand that. Okay, let's look at RE. Okay, how that equivalent small signal RE. RE is a little, calculation of that is a little less than straightforward. Okay, but what we can see is RE looking in to the emitter. When you're looking into the emitter with a base resistance and collector resistance, with the base and collector resistance, what you will see is R pi plus RB by beta plus 1. Earlier we had looking into the base, RIB, looking into the base, RIB was R pi plus beta plus 1 times RE. Okay, when you're looking into the base, you're looking into the base, I'm sorry, this R pi is added to RE plus. But if you're doing it the other way around, if you're looking into the emitter, is the resistance in the base, see what happens. Okay, what you get is R input looking into the emitter is R pi or RB plus R pi divided by beta plus 1. Okay, so the idea is when you're looking into the base, the resistance is multiplied to be a large number. When you're looking into the emitter, it appears to be a small value. Okay, when you're looking into the emitter, this R pi plus RB divided by beta plus 1. Okay, divided by beta plus 1. And you multiply that by RC over R naught. Okay, you multiply that by RC over R naught. Typically, RC is smaller than R naught. Okay, RC is smaller than R naught. Okay. So the resistance in the base is reflected down. So it's reflected down, meaning that it is divided into the emitter by dividing it with beta plus 1. Okay. So there are 3 resistances. So when you see that RC tends to infinity under some limiting conditions, that beta plus 1 vanishes, you simply have R pi plus RB. So the idea is we looked at 3 resistances. Okay, R input looking into the base. Okay, R input looking into the collector, and R input looking into the emitter. Okay, R input looking into the collector is R naught, what was initially there, that is multiplied by 1 plus GM times R emitter. Okay, that is emitter resistance actually increase the RIC. This guy R pi plus 1 plus beta times R emitter. Okay, that's RIB. On the other hand, if you look at RIE, this guy is approximated as R pi plus RB by beta plus 1 small value times 1 plus RC by R naught, another small value. Okay? So 3 resistances that are of importance to us. Okay, so we'll come back in the next class and see how we can use them. Okay, for now, I kind of provided the intuition around why these transistors operate in different configurations, what their characteristics are, what is the salient feature of each of these, what are the advantages and disadvantages of each of those, and then just look at the resistances looking into each of those terminals. Questions?
Yeah, Professor, like for the exam, so like we just need to like go through the final formula that we are getting.
Yes, these formulas, okay, these ones, okay, these are the ones that you want to pay attention to. We'll nevertheless go through the analysis. We'll go through the analysis to actually see how this result came about. But what you want to understand is that there's only these formulas that are important to us: RIB,